Hey, what's up guys? Welcome to today's lesson. Today we're going to be learning about scientific notation. I understand that this is probably a new concept for a lot of you, but all scientific notation really is just taking very, very large numbers or very, very small numbers that are less than 1 and rewriting them in a way that saves time and is just easier to make sense of. So, I'm going to start by showing you a bunch of different numbers where we can actually use scientific notation. Facts. The age of the Earth is an estimated 4,600,000,000 years old. In chemistry, one atomic mass unit is 0.0000. You get it? There's a lot of zeros. There's 26 of them. I'm not going to say all of them. It's a very, very small number. There are an estimated 10 quintillion insects alive on planet Earth. Big number. There are an estimated 326 quintillion gallons of water on Earth. It is estimated that the mass of an electron is 0.0000. Again, I'm not going to say it. You get it. It's a very small number. Now, what do all of these random numbers that I just threw at you have in common? Well, let's take a look. They all include either very, very large numbers, so like here and here, or very, very small numbers, so here. These numbers look like they're about to hit 0, but they actually stop down here. Now, how can we write these numbers in a way so that they are easier to say and write? Because looking at these numbers, it looks so easy for me to just leave out a 0 or add an extra one where there shouldn't be. So let's take a look. Each of these numbers is made up of two different types of numbers. What are they? They each have a number part and a 0 part. They all have a really annoying amount of zeros. So see, 0, 0, 0, 0, 0, and here's our number part. Number part, 0 part. So how do we rewrite these? We're going to use scientific notation. Pause the video, write down this definition. Scientific notation is a way to express numbers that are very large or very small. And we'll start looking at this. Scientific notation has two parts. It has a number that is in between 1 and 10, and then it's going to be multiplied by an exponent that always has a base of 10. Always has a base of 10. This number right here will always be 10. Okay, let's start an example. Write the following number in standard form. So I'm given this number in scientific form, and it's asking me to rewrite it in standard form, which is just the number itself, like all of the numbers from our previous examples. So looking at this, I don't really know what this means, 4.5 times 10 to the power of 8, but when I'm looking at this, I only have a 4 in front of the decimal point. And when I'm taking something 10 to the 8th power, I'm essentially shifting this decimal point to the right 8 times. So when I have a positive exponent, I am shifting the decimal point to the right that many times. I'll repeat myself. When the exponent is positive, you shift the decimal point to the right that many times. So let me show you what I'm talking about. I'm going to rewrite my 4.5. Here's my old decimal point, and I'm just going to shift it to the right 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. Here is my new decimal point. And what I'm going to do with all these gaps is I'm going to put zeros here. And I'm filling in these zeros because these are all of the place values we skipped over. And the zeros fit quite nicely. Here we go, and here we go. Wow. So let's clean this up, make it look nice and tidy. I'm going to write 4 and my 5, and I have 7 zeros. 2, 3, 4, 5, 6, 7. My new decimal point's there, and I'll add my commas. So I can say that 4.5 times 10 to the 8th power is the same as 450 million. And that's it. Okay, let's try another one. Now, what is different between this scientific notation and this one? Same form, but in example 2, we are given a negative exponent. And what this means is when the exponent is negative, you're going to move the decimal point that many times to the left. When the exponent is negative, you are going to move the decimal point that many times to the left. And if you think about it, this actually really makes sense, because on our number line, when we have our 0 here, all of the numbers to the left are negative. So I have -1, -2, -3, you get it, it goes on. So it makes sense to go to the left when we have a negative exponent. So I'm going to start by writing out my non-zero numbers, 9.98, and I'm going to shift my decimal point 6 units to the left. 1, 2, 3, 4, 5, 6. Here's my new decimal point, and I'm going to do the same thing, fill in my place value gaps with zeros. So I have 5 zeros, and let's rewrite our answer nice and pretty. 0, 0, 0, 0, 0, 9, 9, 8. This is my final answer, and I can add a 0 right here in front of the decimal point. That doesn't change my number at all. So if I want to write out 9.98 times 10 to the power of -6 in standard form, this is what I will have at the end. At this point, you need to pause your video. Let me pull up these problems for you to solve. Try these problems on your own and compare your steps to mine. Hopefully your answers look something like mine. I'll quickly explain what I did. So first I decided which way I was going to shift my decimal point. I'm shifting it 5 units to the right because it is a +5 in my exponent. And so what I did is I shifted it 1, 2, 3, 4, 5 units to the right. I filled in zeros for my place values, and I rewrote my answer as 820,000. I did the exact same thing here, except because I have a negative exponent, I'm shifting it that many times to the left. So I rewrote my 4.4, and I shifted my decimal point 12 place values to the left and rewrote my answer. Now, it wants us to write the following number in scientific notation. So instead of starting off with standard form, instead of starting off with scientific notation and going standard form, we are working in reverse. And this really isn't that much more difficult. All we're doing is trying to get the non-zero numbers away from all of the annoying zeros. And so what we're going to do is we're going to place our new decimal point. Our original decimal point is here, but we're going to place our new decimal point to where there's only one number in front of it when we're separating the non-zero numbers. So I'm going to rewrite my 4.6, okay, and I'm going to count how far away my new decimal point is away from my old decimal point. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. I went 9 over. So I have 4.6 times, this number is always 10. You never even have to think about what this number is going to be. It's always going to be 10. 4.6 times 10 to the 9th power. That's your answer. Easy peasy. And it's a positive exponent because my original number is greater than 1. So, here's another one. Write the following number in scientific notation. Here's my original decimal point, and I'm going to place my new decimal point so that there is only one number in front of it. I'm going to Remember, all we're doing is separating the non-zero numbers away from all of the annoying zeros. So I'm going to rewrite it as 3.26 times, and let's count how far away my new decimal point is from my old decimal point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 place values over. Wow, big number. So when I rewrite this in scientific notation, I have 3.26 or 3 26/100 times 10 to the 20th power. Boom, that's it, you're done. At this point, you need to pause the video, try these practice problems on your own, and then compare your answers to mine. Okay, so hopefully you attempted those problems on your own. If you did, your steps should look something like mine. So I'll break it down what I did very quickly. I first moved my old decimal point into a place where there is only one number in front of it, giving me 9 87/100. I then counted the place values away from my new decimal point to my old decimal point and counted 1, 2, 3, 4, 5, 6, 7, 8. And then I rewrote my answer in scientific notation as 9 87/100 times 10 to the 8th power. Exact same steps on this side. I rewrote my number so that way it is separated from the zeros and there's only one number in front of the decimal point. 3.768. I then counted the place values and got 12, giving me 3.768 times 10 to the 12. If this doesn't make sense, please stop the video, go back and rewatch, try the problems again. Okay, example 5. Write the following number in scientific notation. Actually, we're going to skip this one. Example 6. Write the following number in scientific notation. So this is, again, the same steps, but we just have a number that's less than 1. So we're going to work backwards. We're still going to separate our non-zero integers from our zeros, and we're still going to put the new decimal point in a place where there is only one number in front of it. And again, let's write our new number, 4.65793. And let's count how far away our new decimal point is from our old decimal point. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 9. So our new answer in scientific notation is 4.65793 times, our base is always 10 no matter what, 10 to the negative 9. It's a negative exponent because our answer is less than 1. Okay, that's it. Easy peasy. At this point, you need to, here, let me pull up the problems for you to solve. Pause the video, try these problems on your own, and compare your answers to mine. Hopefully your steps look something like mine do. I did the exact same thing as before, separated my non-zero numbers from my annoying zeros, and moved my decimal point so that way there's only one number in front of it, the 1, and I got 1.2905. I then counted how many place values away my new decimal point is from my old decimal point, and I got 7 place values. When I'm rewriting my answer, I have 1.2905 times 10 to the negative 7, and it's negative because my original standard form number is less than 1. Same process over here. I separated my non-zero integers away from all of my annoying zeros, giving me 1.009. I counted the place values. It is 17 place values away from my old decimal point, giving me 1.009 times 10 to the negative 17. This concept takes a lot of practice, you guys, so if you're not getting it at first, don't be discouraged. Keep practicing. Message me or Ms. Youngward if you have any questions at all. that is the end of this video. I hope you guys have a wonderful day.